Start one important topics related to Gram-Schmidt orthogonalization process. Okay, we also discuss one theorem related to that. Okay, we also discussed this one in our previous class, but today we just write the statement of this theorem. We write it now. Let W be a finite dimensional subspace, finite dimensional subspace, okay, of an inner product space V, of an inner product space V. Understood? And let Y belongs to V, and let Y belongs to V. Then there exist unique vectors U, unique vectors U belongs to W, okay, and Z belongs to W perp, okay, such that what happen, y equal to u plus z. Understood? And furthermore, okay, if v1 v2 vk, okay, is an orthonormal basis, is an orthonormal basis, okay, for W, then what happen, then u equal to, here I equal to 1 to k, okay, y vi, here vi, okay. Then what happened, we also do it easily. We also proved that in previous class. Now we're going to discussion one corollary related to that, okay. What this one says, that W be a finite dimensional subspace of an inner product space V, and Y belongs to V, then there exist unique vectors U belongs to W and Z belongs to W perp, such that Y equal to U plus Z. Understood? And furthermore, if V1, V2, Vk is an orthonormal basis for W, then U equal to I equal to 1 to K Y Vi. Okay, inner product of Y Vi Vi. Okay. Then we also discussion on corollary, okay. Here the vector u, okay, the vector u is the unique vector, in W, okay, in W, that is closest to Y, that is closest to Y. Understood? That is closest to Y, that is, okay, that is what, for any x belongs to W, for any x belongs to W, okay. Here norm of y difference x greater than equal to norm of y difference u, okay. And this inequality is an equality if x equal to u, and equality hold if x equal to u, okay. Understood? Not a problem at all. Now we're going to prove of that. We now erase that portion and going to prove of that, okay. So we prove this corollary now, okay. Then we write here proof, and we're going to discussion proof of that. So here we have we have y equal to u plus z, where u belongs to w and z belongs to w perp. Okay, let x belongs to w, and then what happened? Then u difference x obviously belongs to w is orthogonal to orthogonal to z. This one is too easy since u difference x belongs to w. Okay, and z belongs to w bar. So this one u difference x z is 0. Understood? Now then what happened? Then we do going to discussion here. We have what here? Mod of norm of y difference x square equal to, here y equal to what? U plus z difference x square. Okay, this equal to what? This equal to u difference x plus z square. This equal to what? This equal to u difference x square plus z square. Okay, this equal to what? This greater than equal to mod z square. This equal to what? This equal to y difference u square. Okay, then what we write here? Then we write here in this way. Now suppose that now suppose that here norm of y difference x equal to norm of y difference u. Okay, then the inequality becomes an equality, and therefore what happens is here u difference x square plus z square, okay, equal to here norm of z square. Since this one u different y difference u equal to z square, and here y difference x equal to u minus x whole square plus z square. Okay, then this implies what? This implies norm of u difference x equal to 0. This implies what? This implies x equal to u. Okay, then what happens is here, then we also prove this one. Okay, that means this one y difference x. Okay, here we write norm of y difference x greater than equal to norm of y difference u, and equality hold for x equal to u. Okay, and equality holds for x equal to u. Understood? Then what happened is here we also discuss now the vector u. We erase that portion and going to further discussion of that. I think this one is too easy and we also discuss too easily. Okay, now we erase that portion and going to further discussion on that. Okay, that means we have to talk about that the vector u is called the orthogonal projection, is called the, okay, orthogonal projection of orthogonal projection of y on w, of y on w. Okay, then what happened is here we also talk one theorem. Now we write one theorem. Okay, related to that. here suppose that okay is equal to v1 v2 vk. Okay, is an orthonormal set, is an orthonormal set, okay, in an n-dimensional inner product space V, in an n-dimensional inner product space V. Okay, then what happened? Then first one, S can be extended to an orthonormal basis, to an orthonormal basis. Okay, v1 v2 vk plus 1 vn. Okay, for v and p, if w equal to span of s, okay, then s1 equal to here vk plus 1, okay, vk plus 2 vn, okay, is an orthonormal okay, is an orthonormal basis for w perp. Okay, now we write C here. If wb is any subspace, okay, of v, then what happened? Then dimension of v equal to, okay, dimension of w plus dimension of w perp. Okay, now we also then discuss this one. Here S v1 v2 vk is an orthonormal set in an n-dimensional inner product space V, and then S can be extended to an orthonormal basis, here v1 v2 vn for V, and if w equal to span of S, then S1 equal to is an orthonormal basis for w perp. If w is a subspace of V, and then dimension of V equal to dimension of w plus dimension of w perp. Okay, now we erase that portion and going to further discussion of that. That means we're going to prove of that. Okay, we write it here, proof. Okay, here A, S can be extended to an order basis. Okay, by replacement theorem. Okay, by replacement theorem, S can be extended, X can be extended to an order basis, S dash, okay, S dash, or v1 vk vk plus 1 vn. Okay, understood? Then what happened for V? And now what happened? this can be sorry, here wk plus 1. Okay, here wk plus 1 wn. Okay, in obviously in replacement theorem we also see that. Okay, that means v1 v2 vk and w1 w2 wk. Okay, we also see this one. That means in replacement theorem we use this one. That means what is here, that means v1 v2 vk, obviously that means basis for v1 v2 vk are basis for v. Okay, and w1 w2 wk. Okay, w1 w2 wk obviously here, that is for basis for basis for what, w perf. Okay, then what happened, then here we apply Gram-Schmidt. Okay, Gram-Schmidt process to S dash, Gram-Schmidt process to S dash. Okay, then the first k vectors resulting from this process are the vectors in S. Okay, the first k vectors are the vectors in S, and this new set span V, and this new set spans V. Understood? Then what happened, normalizing last k, normalizing last n minus k vectors. Okay, normalizing last n minus k vectors of this set produces an orthonormal set, produces an orthonormal set. Okay, then we write it here. Okay, that means normalizing these vectors produces an orthonormal set that spans V. Understood? Then what happened, then obviously we'll see that. Okay, then this one v1 v2 vk. Okay, and vk plus 1 vn. Okay, this sets obviously basis for v. Okay, this set is an orthonormal basis for v. Understood? Now we also, that means erase that portion and going to further discussion of that. Okay, then now we write here to B. Okay, option B, and going to discussion that what, that means vk plus 2 is an orthonormal basis for W perp. Okay, because we write here, because this one is a subset. Okay, this one is a subset of a basis and it is linearly independent. linearly independent. Okay, then what happened? Since S1 is clearly a subset of W perp. Okay, we need only so that it spans. We need only so that it spans W perp. Okay, then what happened is here. Note that for any x belongs to V, we have, okay, x equal to what? X equal to I equal to 1 to n, inner product of x vi. Understood? If x belongs to W perp, okay, then what happened? Then x vi equal to 0. Okay, for 1 less than equal to I less than equal to k. Therefore what happened? Therefore here x vi, okay, belong to span of S1. Understood? Then we also done this one. Okay, that means x1, x2, here xk plus 1, sorry, vk plus 1, and dot 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 vn is an orthonormal basis for orthonormal basis for, okay, for W perp. Understood? Now we erase that portion and going to further discussion of that. Okay, we write here C, let W be a subspace of V, okay, it is a finite dimensional inner product space. It is a finite dimensional inner product space. It is a finite dimensional inner product space because V is understood, and so it has an orthonormal basis, and so it has an orthonormal basis. Okay, v1 v2 vk, v1 v2 vk. Okay, then what happened? Then by A and B we get what? Dimension of V equal to n equal to k plus n minus k equal to dimension of W plus dimension of W perp. Okay, understood? Now we're going to discussion on example. here let W equal to span of E1 E2. Okay, in FQ. Then what happened? Then x equal to a b c belongs to W perf. Okay, if and only if and only if 0 equal to x e1 equal to here a and 0 equal to x inner product e2 equal to b. Okay, then what happened? Then obviously we write it in this way. Therefore W perf equal to span of e3. Okay, since x equal to here 0 0 c. Okay, so this one. Then what happened? That means e3 belongs to W perf. Okay, so dimension of W perf is 3 difference 2. Okay, then dimension of W perf equal to what? The dimension of W perf equal to 3 difference 2 equal to 1. Understood? Then what happen is here, that means we also see that, okay, dimension of W perf equal to dimension of P difference dimension of W. Okay, we write it here, dimension of W perf equal to dimension of P difference dimension of W. Okay, so today I stop here. If you get this type of video, please subscribe my channel. If you want to give like, please click on like options. If you have any question, comment, suggestions, write it in comment box. So today I stop here. Thank you.